Welcome back to ECE 442, 542. We're all sort of congregated in this class. I'll try not to step on anyone today. It's pretty heavy attendance. It's on design day, but we will proceed anyway with the high attendance. And we appreciate those that did appear. For those that are finishing up their senior project, they may not have to worry about this, but 542 is having their project due on Wednesday. Maybe you're doing both, and just keep that deadline in mind. We also have the teacher course evaluations. We haven't yet approached that 80% limit, that threshold. We're not quite even half there the last time I checked. So if you're looking for extra credit based on TCEs, we need to really involve your neighbors or get them to actually submit their TCEs. And that is useful information actually for me to try to determine what worked for you, what you think could be improved upon, how can we now enhance the class moving forward. Our final exam is the last day of finals. It's on Thursday, the 10th of May, and it's going from 1 p.m. to 3 p.m. in this room. It won't change anything. We'll talk a little bit more about that. And I actually haven't planned a review session since it's during finals week. Maybe I will have something, or maybe I'll just post one from a previous year. I haven't yet decided. I don't know if you would want to attend, if I would try to have a review session or not, but just be aware the final exam is comprehensive. It will include material from Unit 7 and Unit 8, or Homework 7 and Homework 8, and Homework 8 might have as many as 2 problems or so out of 15. So I'm expecting about 15 problems instead of 4 or 5, but in some of those 4 or 5 problem exams that we've had, they've had a couple of pieces. So that's like 10 problems, 2 times 5 in the 75-minute time frame. Now you have the full 120 minutes to do the final exam. And you'll have one more sheet of notes in addition, handwritten notes or your own notes in addition to the tables, and any of the equipment that you want to bring: compass, protractor, ruler, straight edge, etc. As I've said before, homework number 8 is due on that reading day, the day after our last day of class, and because it's due this week, I'm making it extra credit. If you want to do it for extra credit, you can submit it by the 3rd of May. If you don't want to worry about it until prior to the final, that's okay. It won't hurt you, but it will hurt you if you don't know the material going into the final exam. The material on homework number 8 will be included on the final exam. The lower half of the screen that's now being displayed contains the office hours for the coming week, and we'll have Wednesday's office hours from 12:30 to 2:30. On Friday, the hour of office hours has been slid from the normal time. Again, I have another couple of appointments on either side of that, so it's at 10 o'clock to 11 o'clock on Friday. And then the remaining office hours are 2-hour blocks, but they're during finals, so hopefully I'm not overlapping all of your final exams. I think I've selected those so that it's not during one particular final exam period. But those are then on Monday, Tuesday, and Wednesday, and our final exam again is on Thursday of next week. If we need to quickly say continuous time state space or discrete time state space, that will be CTSS or DTSS. And what I want to do today is actually review where we've been with Unit 8. Unit 8 is state space design techniques, and we've talked about full state feedback. That's where you actually have all of the state variables available to you. You can measure those, scale them independently, and inject those or sum those up to form your input signal U. And here, we've been talking about U is equal to minus Kx, and there's no external reference input signal. And I was thinking, how could I maybe communicate that to you? And now the K, the full state feedback, is really telling the system how to behave. So we've talked about deadbeat in terms of maybe the personal side of deadbeat. Well, now we're talking about behavior. If you had behavior in people, now getting them to behave is basically selecting the K matrix. We'll then tell them where to go in finding or using the reference input, and that will be after we've talked about behavior. Behavior just says behave, and it tells us how to move. But then how do we move to a different location? Where do we, if we're going to 10 degrees or if we want to go to 14 miles an hour, that's telling us where to go. That's when we want to inject a reference input or an external reference input. Or K, this full state feedback matrix, influences the behavior of the system, the dynamics, and in order for our system to be arbitrarily capable of being controlled or told how to behave or be able to behave any way that we want, and now you can think about the performance specifications. How do you select those desired locations the way you want? You do that through K, but how does a system allow you to do that? Well, if your system is controllable, you can now have total freedom on selecting the behavior of your system. And we'll talk about how you can check a system's controllability in today's class. How do you build that up? It's really just creating a matrix, and for a single input, single output system, we simply need to take the determinant of that matrix, and then if the determinant is non-zero, it could be negative, it could be positive, but if the determinant is non-zero, our system is controllable. It's a fairly straightforward process to check whether or not we can arbitrarily select the behavior of our system through the choice of a K matrix. That's assuming that we have the full state vector available to us. If we now have the full state feedback with a reference input, now we can tell the system where to go. With K, we're telling it how to behave. With the reference input, we're telling it how or where to go. And if you need help with homework number 8, I think the example that's illustrated in lecture 8.3, which is a mass spring damper, it develops the model. It talks about how to find the full state feedback gain matrix K, and it illustrates how to do that using MATLAB. And that might be helpful in solving homework number 8 problems. Here's our review from last time. We now are talking about time domain state space representations, where we could think of this state vector x being so many state variables tall. And those state variables might be position, velocity. In the mass spring damper system, it's position and velocity. That's your state vector. And those now combine with the input through the input matrix gamma. And gamma has to be compatible with the number of state variables and the input. And the input now we're assuming is Michigan tall. In this class, a lot of times M will be 1, we'll have one input. And a lot of times in this class, Q, the dimension on our output will be 1. We'll have a single input, single output system. And that simplifies things, and it gives us enough to work with in terms of what we want to better understand using these concepts of state feedback design. In terms of an arbitrary number of inputs M, Michigan, and states N, Nevada, our state vector feedback matrix K is a matrix, and it's M by N. And that's our matrix feedback gain that connects all of the state variable components into the input vector U. I actually sort of like to have a visual of those algebraic equations. This block diagram helps that process. In terms of here, when you see the delay, think of the number of delays as equal to the number of state variable components you have, or N, Nevada. So that delay block is actually a big block, or could be, if you had 10 state vectors, components. So if you had 10 state vector components, your delay block would consist of 10 different delays. And how those are interconnected is influenced by your system matrix phi. You inject information through the input matrix gamma, and here with full state feedback, we're assuming we can go in and access that entire state vector x, x sub 1, x sub 2, x sub 3, feed that back through this gain matrix K, and create the input U of L is equal to minus K x of L. And I've tried to, it didn't highlight very well, but hopefully you can see that over here we're missing the reference input. There's nothing being injected in to tell this system where to go. Right now we're just changing the behavior of that system through the gain matrix K. K just tells the system how to behave. So if you didn't like the percent overshoot, if you didn't like the settling time, you didn't like the peak time, you could reposition the closed loop eigenvalues through the selection of that gain matrix K to adjust the behavior of your closed loop system's dynamics. But without anything else feeding into that summing junction to make the input U, when we have no external reference input, we can't command this system to move anywhere. Now it's just responding to initial condition offsets or offsets in our state variable components. Or if you walked up and kicked that system, it would behave the way you want it to behave in response to those offsets in state variables. And you would be trying to drive all of those state variable components to 0 with the choice of that full state feedback gain matrix K. When we speak of how the system behaves nominally in the open loop without that K, that's influenced by this system matrix phi. And you can maybe see that why that is the same as the eigenvalues of phi if you think about what this transfer function g of s or g of z actually looks like. What's the inverse of a matrix consist of? Or if you now needed to perform the inverse of this matrix zi minus phi, what pieces would that consist of? Pardon? I think I heard it. There's a determinant involved, and where is the determinant? It's in the denominator of that inverse matrix. And g of z is a rational expression. And that denominator equation is that determinant equation is in the denominator. Because the determinant of zi minus phi is in the denominator of this operation of an inverse of that matrix. So if you looked at this in terms of an expression, you would say now you have this adjoint matrix of zi minus phi, and that's going to be some square matrix as a function of Z, but it will now collapse when you pre-multiply by the output matrix H and post-multiply by the input matrix gamma, and that will now become the numerator polynomial, and that's going to be on top of the determinant, which is Zi minus phi. And that's all buried inside or as a part of this expression, Zi minus phi inverse. The key to finding the poles, the natural behavior without controlling the system, the open loop dynamics, are contained in the denominator of g of z, and that's actually equal to the determinant of Zi minus phi. That influences the open loop dynamics of our system. And now we simply have to be able to compute the eigenvalues of a matrix. And on the final, since you have 2 hours for the final, you should be able to do a symbolic determinant matrix, or determinant symbolically of maybe a 5 by 5 without too much teasing. But you should be able to do a 2 by 2 determinant. And here I'm illustrating what that looks like. The identity matrix needs to be compatible with the system matrix phi. Phi in this case is 2 by 2. And we end up then with the determinant being the product of the diagonal terms minus the product of the off-diagonal terms. And in this case, we have a 0 on the off-diagonal, so those disappear, and we just have the product of our diagonal terms, which is z times z minus 2. And the values of z that cause that to vanish will be your eigenvalues of the system matrix phi, the open loop system matrix, but those are also the poles of your open loop system. And that's what I'm trying to illustrate here by the arrows connecting the different pieces. You can make that polynomial, that second order polynomial, you can make it vanish 2 different ways. You can make it vanish by setting z equal to 0, or you can make it vanish by setting that second factor equal to 0, which would be when z is equal to 2. Those are your open loop eigenvalues, and many times those are not in an acceptable location. In this case, 1 is beyond the unit circle. The one at 2 is unstable, so if somebody walked up and hit this system without any feedback, it would start going unbounded. That mode at 2 would just keep growing, 2, 4, 8, etc. 2 to the n. That's why we might want to introduce full state feedback, which now says let's take the full state vector x, scale it independently with different elements in K, and combine those to form the input U of L. The full state feedback is allowing us to influence the system behavior. So if we tell the system to behave, we're actually designing this full state feedback gain matrix K. And if we say behave, that means that we're interested in maybe changing the percent overshoot, the settling time, the peak time, etc. And so we're using K, this matrix, and a lot of times in this class, if we have one input, that K matrix is actually going to be a row vector. It's going to be one row tall, and it will have as many columns as we have state variable components. If I say I want those, or I want to select K, or pick U, or use U to create desirable closed loop pole locations, that's now really circling back to earlier concepts that we've talked about in this class, and how do you pick more acceptable locations for your closed loop poles or the behavior of your system. Maybe you say, oh, I want a particular type of overshoot, or I want a given settling time. And we know what shapes are associated with those particular performance specifications. Circles, concentric circles, the closer we are to the origin, the faster or the slower our response. If we get closer to the origin with our dominant poles in the z-plane, what's our behavior? Is it faster or slower? The closer we get to the origin, the faster our system is going to behave. These concentric circles, getting close to the origin, is going to speed up our system response. Hearts, how do we want our hearts to be shaped or adjusted if we want less overshoot? Do you now have a mental image of what these hearts look like? What's a heart shape, or what's our heart shape when zeta, the damping ratio, is 0? What does our heart look like when zeta is equal to 0? Pardon? When zeta is equal to 0, zeta equal to 0 says no damping. What would you think, where do you think we would live with our poles or our desired poles if we had 0 damping? If we had no damping, nothing damps, then where are we living in the z-plane? Right on the unit circle, right? So our poles are on the unit circle. Our heart's not much of a heart for zeta equal to 0. It's actually a circle. And then as we increase zeta, then we start seeing hearts. But as we get zeta closer to 1, that heart starts collapsing to a straight line. When zeta is 1, that's when we're on the real line between 0 and 1. And then we have an exponential behavior. But those different shapes should inform our choice of what we want our system to behave like. And the angle of that those poles make, and now we're really sort of talking about or focusing on 2 dominant poles. If we had a fifth order system, how would somebody go about selecting what's a quick way for the final exam to select dominant behavior or the locations for those 5 poles? So we would probably make 2 of those achieve certain settling time, percent overshoot, or peak time behavior, and the other 3 we would make deadbeat. We would locate those 3 at the origin. Then we quickly have our dominant poles by those 2, and the other remainders, which in this case, if we had a fifth order, we would want 2 to be dominant, then the other 3 would be at the origin to be a deadbeat. And now we have our fifth order polynomial. We have z cubed times a quadratic in z, where that quadratic in z is determined by this coordinated collection of circles, hearts, and angles. And that gives us this delta sub d. That's our desired polynomial. The other polynomial contains the unknown coefficients in our full state feedback gain matrix K. And if we had a fifth order system, then we would have K sub 1, K sub 2, K sub 3, K sub 4, and K sub 5. We would need to solve for all 5 of those consistent with whatever would produce this delta sub d, the desired polynomial. In our example that we looked at last time, we just sort of, in fact, reached up in midair and grabbed two complex poles, one, and they're conjugate, because we wanted to have real coefficients in our second order polynomial. We picked those complex conjugate poles to be at 0.8 plus and minus j.2. Those are our desired dominant poles, and now we can figure out what that corresponds to in terms of polynomial. And here I'm just showing you, sort of reminding you of how that start here arises, but it's really the FOIL, where the outer and the inner, the cross terms, cancel because of the complex conjugate behavior of your poles. And I tried to sort of step that through visually in the top three lines of creating or building that desired polynomial, but you don't have to do that on the exam. If you now know that you have complex conjugate poles, then you can, in rectangular form, immediately say, oh, here's my real part of those conjugate poles, and here's my imaginary part, and put it into this z minus 0.8 quantity squared plus 0.2 squared form. Is that clear? And if you now see a polynomial written in that form, you know immediately where those poles are located. You could have z plus 0.8 squared plus 0.2 squared. Where would those poles be? Those would be in the left-hand plane, but they're still inside the unit circle, so they're allowable. It's just that they're maybe a little bit more violent than what you would want. They're quickly changing because now they have real part that would be negative. Z would be at minus 0.8 to solve that polynomial. If we start here with these complex conjugate poles, we can multiply those out and find the coefficients that we want, that we desire in our closed loop system. Now we want to have our closed loop system having a denominator polynomial or poles such that the denominator polynomial is z squared minus 1.6z plus 0.68. If that's the case, we know that we have poles at 0.8 plus and minus j.2. That's based on circles, hearts, and angles. Really, this delta sub d. That's where we want our poles to be. Now we have to compare that with where these k's enter into the polynomial coefficients in our zi minus the full state feedback system matrix phi sub c. And here I'm just trying to explicitly show or illustrate where all of those pieces arise or where they come from. Our original system matrix that governed the behavior of our system is right there. There is our phi. Then we have our gamma matrix, which was 0, 3. We have our full state feedback gain matrix, k sub 1, k sub 2. We don't know what those are. That's why we're building this up, so that we can determine what k1 and k sub 2 need to be. A few more steps, which you don't have to include all of these steps when you're doing this on the exam, but I'm trying to show you if you don't understand where everything's coming from, hopefully this will make it clear. We now have a 2 by 2 matrix that contains z, and we now want to create a second order polynomial that's not only in terms of z, but also has these k's floating around in the different coefficients. We use exactly the same formula for the determinant here as we have all along. We take the product. This is a 2 by 2. We take the product of the diagonals and subtract the product of the off diagonals. And that then gives us, finally, a z squared plus a coefficient multiplying z plus a constant coefficient. And those coefficients in general could contain k1s and k sub 2s. In this case, our linear coefficient, the coefficient that is scaling z, z to the 1, only contains one of those full state feedback gain component values. So now we have one equation and one unknown, and we can really solve these two equations and two unknowns in a sequential fashion and simplify or make the analysis a little easier and not have to do two simultaneous equations to find those two unknowns. But is it clear that now we want to compare this coefficient with that coefficient and compare this coefficient with that coefficient? That's what we're doing when we say we want to make our controlled system behave like the desired polynomial that we selected based on hearts. I wanted to say hearts, moons, and clovers, but I'm hungry. So I'll say hearts, circles, and angles. Nobody else caught that, but we'll move on. Here's what we're doing. We're simply equating the desired polynomial with the polynomial involving the k's, blues and purples. If we look at the first, comparing the coefficient of z to the 1, the first power of z, then we can solve that for k sub 2, and k sub 2 now becomes 0.133. Once we have k sub 2, we can use that when we're trying to solve for k sub 1, and we can find an equation for k sub 1, or that contains k sub 1, when we compare the constant coefficients. And now we need to set 3k1 equal to 1.48, or roughly 1.5 equal to 3k1, so k1 is about a half. It's just under a half, and it's at 0.4933. We now have a k sub 1 and k sub 2. There's our full state feedback gain matrix. You give me x sub 1 at each time step. I'm going to scale it by almost a half and use that to inject into my system, along with measuring x sub 2 at each time step, scaling that by 0.133, and adding those two together, and that now creates my input, U of L, at each time step. In full state feedback, then, I'm assuming I have access to the full vector, state vector. And now I'm just going to essentially check the answer in the back of the book. Let's go ahead and plug that in algebraically. Let's see if we plug in that full state feedback gain matrix K into these equations, that we do get a closed loop system matrix, capital Phi sub C, with those eigenvalues at 0.8 plus and minus j.2. The blue is just our dynamic equation. That governs the dynamic behavior of the system without any feedback. Once we change or introduce full state feedback, then we are really shaping the input to that system as a linear combination of state variables. And this now should convince us of the dimensions of K. K has to be compatible with gamma and phi, meaning the product of gamma and K needs to be phi, the same dimension as phi. If phi was 1 by 1 and gamma is a single input system, then what are the dimensions on K? It's 1 by 1, it's a scalar. So it could be that even in full state feedback, you could have K being a scalar. This combination of phi minus gamma K, that's our closed loop system matrix, capital Phi sub C. We've now changed the behave. So now the system behaves according to circles, hearts, and angles. That's working, that's behaving the way you want it to, assuming we have full state feedback. So if you kicked that system, it would behave the way you wanted it to behave. It would no longer behave like the open loop system, phi. Now we've changed its dynamics with full state feedback. And if we return to our example, we have now changed phi, the original open loop system matrix, which was 2, 1, 0, 0, into phi sub C, which is now 2, 1. And why did we not change the top row in phi sub C? Why did that not get modified with full state feedback? Pardon? Because if you look at the top row in the input matrix, you're not injecting any information into that top row because it's 0. The input matrix actually tells you how you're injecting information into the system. How are you influencing each state variable component? The output matrix actually says how am I extracting or pulling information from the system to produce the outputs. But here the gamma is 0 in the top row, and so you're not changing anything in the original system matrix phi's top row. You are injecting information into the bottom with a gain of 3. And that's now where we changed these all zeros in the phi matrix, the open loop phi, into something different. And without doing any other analysis, you know what the eigenvalues of phi sub C are. If your work, your algebra before was accurate or correct. What are the eigenvalues of phi sub C supposed to be? What's the answer in the back of the book? Where did we set those? With this choice, so here is our full state feedback gain matrix K, and we found those entries, K sub 1 and K sub 2, to produce eigenvalues at 0.8 plus and minus j 0.2. That's how we found those K1 and K2. We've now simply plugged those in to create a full state feedback or a closed loop system matrix, phi sub C, with full state feedback. If we look at the eigenvalues of that phi sub C matrix, again, it's just the determinant of a 2 by 2 matrix, product of the diagonals minus the product of the off diagonals. We better end up with a polynomial, second order, that's consistent with those eigenvalues or with those poles. And in fact it is. We end up with z squared minus 1.6z plus 0.68. If you wanted to, you could complete the square from that, and you could say, oh, what times 2 would give me 1.6? That's now my z minus 0.8 expression. and then I have to adjust what is 0.8 squared. Well, that's 0.64. I now need to add in 0.04, which is actually the 0.2 squared, or the square root of 0.04 is 0.2. And now that is our desired closed loop set of eigenvalues or poles. We've now verified our work by looking in the back of the book, figuratively. When can we do this? When is it possible to be able to adjust the behavior of your system arbitrarily? When can we tell this system how to behave, and we can make it behave however we want it to? Do you remember what we said we were going to talk about or show at the beginning of class? No hints allowed. We want to have a system that's controllable. Controllability of our system allows us to use K, full state feedback, to adjust the behavior of capital phi sub C arbitrarily. We can locate the eigenvalues of that phi sub C matrix arbitrarily if our system is controllable. And now we want to talk about what does it mean for a system to be controllable, or controllability. We're really looking at this question. When is it possible, using full state feedback, to position the closed loop eigenvalues or poles arbitrarily? That's what controllability is dealing with or working with. If you now are talking about controllable, if you can control something, then that means you have a lot of power over that system. And that's what this means. You now can manipulate the closed loop eigenvalues to be wherever you want them to be. Maybe you want 2 to dominate and 3 to be deadbeat. Maybe you want 2 to dominate and 2 more to be a little bit less dominant, but still complex conjugate. You have that power if your system is controllable. Or another way of asking the same question is, when can the closed loop behavior of the system be anything that you want it to be? You could actually make it unstable if you wanted. Probably not what you want, but you could. You could create an oscillator. How would you create an oscillator? How would you create an oscillator? If I gave you a system on the final and I said, I want you to build me an oscillator, what would you do? You would want your poles to be on the unit circle, wouldn't you? And if it's oscillating, you probably want it to be not oscillating with no frequency. Where would that be? At 1. So if you put all your poles at z equal to 1, then you're just, what? You're stuck. You're just responding. You just put out exactly what was put in. But if you put them somewhere on the unit circle, then they're going to just continually oscillate back and forth. The period of that oscillation is going to be influenced by the angle that those poles make with the positive real axis. That would influence your theta sub d, which theta sub d is radians per sample. That's how you sort of march around your system or oscillate in your system response. So the answer to those two questions is when the system is controllable. If you have a controllable system, and maybe on the final I'll say, is this system controllable? You'll just have to redo these steps that I'm now going to illustrate for the system that you are presented with. So a system is controllable if and only if we build up this controllability matrix, which I'm calling script C, and that's made up of a collection of columns. So we are going to now just start packing columns into this controllability matrix, and the very first set of columns is going to be the input matrix. And how many columns are in gamma, generically, that we've been assuming? How many rows are in gamma? How tall is gamma as a matrix? We've been talking about two states, Michigan and Nevada, M and N. How tall is the gamma matrix? Is it Michigan tall or Nevada tall? What influences the number of rows in gamma, the input matrix? Gamma has to be compatible with the equation that it's found in, so you're saying plus gamma U of L. Gamma, the number of rows, has to be consistent with or compatible with the number of elements in your state vector. So it has to be Nevada tall. This controllability matrix has n rows in it, Nevada rows. How many columns does gamma have? We're dealing with two states, and I've already flipped the coin and it's landed on Nevada. The other is Michigan. So it's Michigan wide. And in this class, a lot of times Michigan is 1. But right now, in general, we've now started to build a controllability matrix that's Nevada tall and M columns wide. But now we start packing more columns onto this. And the way that we pack columns is we start combining the system matrix phi with gamma. How many columns did we just add by adding in phi gamma to this controllability matrix? How many columns are in phi gamma? What are the dimensions on phi? It's n by n. It's square, isn't it? And you're multiplying that by an n by m matrix. So you have an n by n times an n by m. Obviously, it has to have exactly the same rows as gamma. That's n. And it actually has the same number of columns as gamma. So here we've just added another m columns to this controllability matrix. And we just keep adding columns by pre-multiplying gamma or phi gamma by phi. So now we have phi times phi gamma, or phi squared gamma. That now puts us with another m columns. And we just keep going. Not very happy with my gammas. And when do we stop? We actually stop adding powers of phi when we get to phi of n minus 1. And n, again, is Nevada. And each of these columns that we're packing on to the right come in sets of m columns. Meaning this controllability matrix, how many of those m sets do we have? We started with one set, but that was phi to the 0. We went phi squared, up to n minus 1. So we actually have n sets of columns, don't we? Because we started with phi to the 0. So we have m times n columns in this controllability matrix. All of that to say this is our controllability matrix. And a system is controllable if and only if C, the controllability matrix, is full rank. Is it clear what we mean by full rank? No. So C is a matrix that is dimensionally n by mn, is what we said. Full rank means that in this case, all n rows of C have to be linearly independent. Full rank means that if, let's just pick some numbers. Let's say n was 10 and m was 5. So now we have a 10 by 50 matrix. We would want this 10 by 50 matrix to have 10 linearly independent rows. Or we could have 10 linearly independent columns. It's going to be full rank if that's the case. In our case, in this class, a lot of times we're going to restrict this to only having one input. Michigan is going to be 1. Little m is equal to 1. So if m is equal to 1, or we have a single input, or we have one input, then this controllability matrix C is square, and we actually need the determinant of C to not equal to 0, be not equal to 0 for the system to be controllable. So if we have one input, when we create this controllability matrix, it's going to be square. Now you just have to find the determinant of that square matrix and hope, well, if your system is controllable, then you're hoping that that system or that determinant is non-zero. If we look at our example that we've been playing with, we had a system matrix, phi, an open loop system matrix that was 2, 1, 0, 0. Our input matrix was 0, 3. Nevada was 2. Michigan was 1. Sounds like a baseball game or a hockey score, huh? Nevada 2, Michigan 1. Now, with those matrices, what does the controllability matrix look like? Stop me whenever you want. I didn't need to put that many columns, sets of columns in, did I? How many do I need? I just need phi raised to the n minus 1, 2 minus 1. I need phi to the 1 times gamma in this example. I just need to make two columns. The first column is simply gamma, that's 0, 3. And the second set of columns, which is just one column, is phi times gamma. And now, depending on how you learned how to multiply matrices, or one way, gamma, do you see, is actually not weighting the first column of phi because there's a 0 in the first row, and it's scaling the second column by 3. So if you think of phi gamma that way, you can say, oh, phi gamma is just 3, 0. I'm just going to scale the second column of phi by 3. And the second column of phi is 1, 0. I'm going to scale it by 3, and I'm not adding any of the first column because the first row of gamma was 0. Or if that doesn't make any sense, just do first row times first column, second row times first column, etc. And you should get the same answer. Now what we want to do is compute the determinant of C, which is now the product of the diagonal minus the product of the off diagonal, and we just need that to be not equal to 0. It's negative, that's fine. It can be negative. But we now know that our system is controllable. Now, if you're still with me, if we have a completely controllable system, are we getting away with something? Now we can change the behavior of our system arbitrarily? We didn't used to be able to do that in the transform techniques. We were restricted by what the root locus looked like. That's where our closed loop poles were, and those were not the entire complex z-plane, were they? Those branches, those red lines on the root locus, were just certain branches, certain locations in the z-plane. Now, if our system is controllable, we're saying we can place our closed loop poles wherever we want. We don't have to be restricted to being on these root locus branches. So the question is, are we getting away with something when we've now switched to doing full state feedback? Or now that we're doing state space representation and control design with state space matrices? Full state is different than what we had before. When we were doing the transform, we were assuming we could only measure the output and scale that or use that in our feedback. Now we're saying we can measure everything in our state vector and use that in our feedback strategy. Meaning, full state feedback requires access to each component of the state vector. So that's actually a big assumption. Now if we had a system, let's say we had a motor, and we needed the temperature of every one of those cylinders in our motor to do the dynamic analysis or to model the system behavior. And maybe we needed velocities and positions and pressures. Well, maybe we don't have access to all of that. But this strategy is assuming we have all the positions, all the velocities, all the temperatures, all the pressures, every one of our state variable components. We're assuming we have. Next lecture, we'll talk about what happens when we don't. Can we still maybe estimate those? Can we somehow create those by an observer or by an estimator? But now we're assuming that we have each state variable component measurable or available to feedback. And that's a big assumption. But if we do, then we can, if our system is controllable, then we can arbitrarily select the behavior of our closed loop system. Are there any other concerns? What are we able to do with full state feedback so far? Behave. Did I scare you? I apologize. We've told the system how to behave, but we haven't told them where to go, have we? We can't tell them where to go without something else. We can tell them how to behave, the hearts, the circles, and the angles. We can tell them that, but we can't tell them go to 10 and lock on or track to 10, or go to 5, go to 50. We're unable to do that. We can't tell this system where to go. We can just tell it to behave, how to behave. So that's something we're missing. The other thing that we're missing is there's maybe uncertainty in our model. Maybe we don't know the phi very well or the gamma very well. Maybe there's some parameters that are varying. That could influence our behavior. But here, let's focus on telling the system where to go. In addition to, I'd hate to throw out the ability of telling our system how to behave. Let's now add on to that. Now we can say, behave, and go to your room. And it will, right? Before we just said behave, and it had to behave. Now we can tell it where to go. And they'll probably tell us where to go when they get to their room, but that's another story. Right? So we can behave and tell it where to go if we introduce a external reference input to our system. So what have we had before? We had a delay, maybe a bank of delays, N of those, Nevada of those, that generate our state vector. The input to that is an advance of that state vector. And building that up, x of L plus 1 is equal to phi x of L plus gamma U of L. And what we've done so far is we've told our system how to behave if it's controllable. We can use full state feedback. We go in and access the state vector and feed that back. The output is right here. But now we want to influence where it goes. And now I'm running out of room on the left. But I want to introduce a reference input. And that reference input, I now want to scale by n sub 1. So now, bummer, I'm going to cheat a little bit, maybe. Maybe I can't. But this signal is now our reference input. We now have our reference input scaled by n sub 1, and that now gets injected in and makes up part of our input U of L. U of L now not only has full state feedback, but it also has an external reference input allowed to it. So here is our non-zero reference input. And so this allows us to tell the system where to go with the non-zero reference input. So now, if the system is controllable, K can adjust. Let me just say K can adjust the dynamics arbitrarily. So we can tell the system how to behave with K. But if we just had K, there's no way to provide a command signal to the system. And if that's the case, then that's a regulator system. If somebody says, I have a regulator system, you're just regulating the behavior of the system. You have no external input. So our regulator system has desired dynamic response to offsets in the state variable components or to initial conditions. So we have acceptable behavior. What we want, it may be, is to have the ability to tell the system where to go. And if that's what we want, then we can introduce a reference input. So can we introduce a reference input? The answer is thankfully yes. So now let's write those equations down that we've now implied by this block diagram. We've sketched the block diagram, but now let's work through that where we now have a reference input with state feedback. Or we are now saying go to 10, we're going to track 10. Tracking a reference input, let's say R of L. And to talk about this, let's go ahead and just assume a scalar input. And this reference input is telling the system where to go. So that now what we are doing is we are going to go ahead and let U of L, we're not going to throw away the full state feedback. That was nice to have. So we're going to have minus K X of L, but now we're going to go ahead and say, add in a little bit more, a scaled version of a reference signal, R of L. And if you wanted to think about what this looks like, let's say we had a single input, U is 1 by 1, but maybe we had 4 components in our state vector. Then we know that K has to have 4 components in that matrix. And if we have one reference input, then N sub 1 is 1 by 1. It has to be compatible. So we have a 1 by 1 times a 1 by 1 is equal to a 1 by 4 times a 4 by 1 to give us again a 1 by 1. Those sum up to give us a 1 by 1. That's what Kx plus Nr could represent. If we work through that, here is our original system. That's x of L plus 1 is equal to phi x of L plus gamma U of L. That's the model of our system. We now want our input to not only tell our system how to behave, but where to go. The behavior of our system is provided by this first term, minus kx of L, and where to go is the second piece. Scaled version of the reference. So that now if we use that U of L in the system equation, we now have our closed loop system dynamics. We have phi times x of L plus gamma times this, minus k x of L plus n sub 1 r of L. And all of these better be compatible with each other matrix-wise, dimensionally, so that we can combine them. So that in this case, we have phi minus gamma k. That's good. That's what we had before. That was our full state feedback closed loop system matrix. That's the matrix that scales the state vector in the closed loop system. And then we have plus gamma n sub 1 r of L. There's how our system behaves, is through phi sub c, and telling us where to go is influenced by n sub 1. That now scales how we inject that reference input into our system. And our output equation hasn't been changed. Y of L is now equal to H x of L. That's our state space closed loop system in the time domain. We now want to put that into the frequency domain. And that's not hard. If we z-transform the dynamics and the output equation, we can find the transfer function between the reference input R and the output Y. Now, if we tell the system where to go, If we say, I want you to go to 10, and we're happy with the behavior, how it gets to 10, we want it to lock on to 10, what do we know about the behavior, the steady state behavior of our system? If we say go to 10 and it actually goes to 10, what have we talked about before when we said, oh, if we put in a constant and we get out that same constant, what particular aspect of our system were we dealing with? We were worrying about the air, and what gave us zero steady state air due to a constant? We needed a DC gain of 1. So now what I may have to do after class is derive the transfer function between the reference input R and the output Y, and show that if we fix the DC gain to be 1 by the choice of n sub 1, that's a scalar in a 1 input system, then we can make our DC gain equal to 1. And when we tell our system where to go, it will go there if we have a DC gain of 1. That will have to be done after class, but I hope you understand what I'm trying to say. We can adjust the DC gain of this closed loop full state feedback system by the choice of this parameter n sub 1. And that's what I want to show or derive after class. But that should help you complete homework number 8 along with lecture 8.3.